let me start by saying, good morning. You have a test next Wednesday, and no, I am not going to push it.
Why?
Why? Because it is timed to fit into this course schedule so that you learn the maximum amount of physics. That is why. Okay. Your third midterm next Wednesday.
Are there any more lessons? Do we have like a new lesson today?
Not a new chapter, but there's new material. That new material. Okay. Next Wednesday, let's see. April 20th. And it's on chapters 27, 28, 29. Yes. All right. Last time we left off with Faraday's law of induction, written in this form, closed integral E dot dl is equal to minus d phi sub b dt, which means it's equal to change in magnetic flux divided by change in time. Let me do an example that they do in your textbook, which is the slide wire generator, or even the slide wire launcher. So I'm going to call it a launcher. You guys can talk about it. So I'm going to start it with a battery. The battery has a certain EMF E, okay? And that battery is going to be connected to a switch. Which is then going to be connecting in two very long parallel rods. And a thicker rod with a length L connects the top and the bottom. So that when the switch is closed, current can flow through the circuit. Current can flow through this rod. Which is all fine and dandy. We close the switch and that would be it, right? Oh, but you know that can't be it now because that was it 2 or 3 chapters ago. So now what we're going to do is we're going to get into this. We're going to put a magnetic field throughout this whole inner region here. So we're going to put a magnetic field here. This whole thing. So we have a magnetic field. And so we're going to see what happens when we close the switch. We first throw the switch, and I guess there's one more thing that we need to know. The long wires have negligible resistance, and the rod has a resistance of R. So that rod has resistance R. And the wires have negligible resistance. Okay, so when you close the switch is closed. Current flows. Okay? Yes?
In an actual application, like when you're in an electrical engineering, would the wires never be negligible, the resistance?
Well, depends on what you made the rod out of. I mean, if the rod is an actual resistor, most wires don't have very much resistance at all. Okay? Usually these would be rails, and then this would be a rod connecting those rails. Okay, because you want that to be staying on here, and you'll see what happens as soon as we get this current flowing here. Okay, so what happens when you get the current flowing is there's a current flowing in this wire. Okay, so we have an initial current. So we have the initial current. Which is equal to E over R. And it flows from the positive side of this to the negative side of this. So you have your current I flowing in this thing. You have current I flowing in that thing. So now so what's going to happen when I do this? Well, I have a current I flowing in this wire here. Everything else is fixed, but the rod can slide. So when I get current in this rod here, there's going to be what? I've got a magnetic field, I've got current, there's going to be what? It recently awakened.
Force.
There we go, there's going to be a force.
Good one. Wow.
All right, here we go. So there's going to be a force on this. Just to keep me from being too, because of my vertically challenged, I'm going to put it, there we go, this is, make this easy on myself. There you go. So I'm going to put my hand in the direction of the current, turn into the direction of the magnetic field. So there's going to be a force on this wire this way. There's going to be a force on that shooting outward. So there's a force on this wire. This. And that's a magnetic force. So what happens is I have a magnetic force. That force on that wire is equal to I multiplied by its length multiplied by the magnetic field. So this starts to move. This starts to move. Okay, so far, okay, keeping up with this. Close the switch, we get a current. A couple chapters ago. Get a current, have a force. Last chapter, or 2 chapters ago. Okay. Now that we have a force, this is going to move. Well, if this starts moving, since I have a magnetic field throughout this whole thing, there's going to be an increase in magnetic flux through that loop. So what that's going to do is that's going to generate an induced voltage. An induced voltage. Now let's figure out what the direction of that induced voltage is. Okay, so when I have a force, this thing's going to start moving. This force is going to generate an induced voltage. What is the direction of the original magnetic flux is which direction? Not down. Don't say down when you mean into the page. There's a difference. Down is this way, into the page is that. Down. Okay. So it's into the page. Is that flux going to increase or decrease? Well, if I pull this out, right, my loop is this after I close the switch. So I'm going to draw this with the switch closed. Close the switch. When I pull this, when this starts moving this way, to the right, does that increase the flux through this loop or decrease it? It increases because the area of that loop is increasing. If you notice as this moves, the area of the loop itself is going to increase. That's going to increase the amount of flux through it. The easiest way to tell is now there's 6 x's. When it moves over here, there's going to be 8 x's going through it, so therefore it increases the amount of flux. Okay? So the third question, in order to fight that increase, which direction does the loop want to put its magnetic field? Out of the page. And so which way is the induced current going to flow? Put your thumb out of the page. Okay. Fingers
back towards the battery.
Counterclockwise. In other words, back toward the battery. So what happens here is there's going to be a voltage induced, an induced voltage that's going to try to cancel this out. As it does, in other words, as this moves, what happens is that there's going to be an induced voltage that's going to try to cancel this out. So the force will be slightly less because we'll start getting less current. Eventually, once this is moving fast enough, they will equal and we'll end up with the terminal velocity. So let's see what happens. So what we want to figure out in this case is because we want to draw this and figure out what's the induced voltage when this thing is moving with some velocity v. We want to figure out what the induced voltage is when this is moving with some velocity v. So in other words, it's going to start moving, it's going to start speeding up. So let's see what happens when we have the same situation here. So here's my regular battery, wire. This is all nice and closed now. I got my V here. And now this is a bit later. I've got this rod over here, and it's moving with some velocity v. And now I want to figure out what the induced EMF is in that rod. The induced EMF. Which is, by the way, is going to be in the opposite sense of the battery. Okay, well, the induced EMF is equal to the number minus number of loops d phi sub b dt. Phi sub b dt. The number of loops in this case is 1. I'll go ahead and keep the negative sign just to remind myself that it's going to be in the opposite direction of our original EMF. Okay, since we know the direction and it's in the opposite direction of this, I'm going to go ahead and keep that minus sign. Okay? So now I want d dt of b a cosine phi. Now, already answered this question before, but let's see if you remember. Does the magnetic field change? No. How about the angle? No. In fact, the angle here is 0 degrees between this. So the factor of cosine phi is 1. B comes out of this thing. And so now we need the area of the loop. Let's see. So let's say that this distance is L, capital L, like so. And let's define this distance here as x. I don't really know what x is because that's going to change. X is going to, you see what I mean? X is going to change. All right, so now let's start writing this stuff out. So minus b comes out of this thing. d dt, the area of this rectangle is Lx. Yes. It's a rectangle. There we go. L does not change with time, so we can pull that out. Minus b, L, dx dt. And, well, I may not know what x is, but what's this? That's the velocity. So I may not know what the x is. So it's B, L, phi. That's the induced EMF in that rod. And so what happens is this continues to speed up if the rods were long enough. You know, I mean, you have to have like long rods, but you could have like a launcher. This could be a nice launcher for you. Turn it on and fires this thing out. Fun. Okay.
It's like a rail gun that the military's.
Yeah, rail gun. Yeah, that's your rail gun. Okay, so it continues until the total EMF is 0, because what happens is that the total EMF around the loop is this minus my BLV, my induced, because they're working in opposite directions. And so as the speed increases, your current is going to decrease. So let me go ahead and solve the current here. So the force becomes less and less. The force on this thing is going to become less and less until what happens? Well, no, not the battery runs out. Until this reaches a speed where this equals 0. In other words, eventually this would go fast enough so that the induced current would be equal to the battery current, which means that they'll just cancel out. You get nothing. You get nothing.
So at that moment, what happened to the rod?
It would just move at a constant velocity. So the final velocity, if the rails were long enough, turns out to be, let's see, so we set this equal to 0. Hang on. Let me write more details here because that's probably confusing. You can edit that out of it. You have to do a lot of editing to edit out all my uhs and and oh and all right, so it continues until this total voltage is 0. So E minus BLV equals 0. It continues until the velocity of the thing is this E over BL. So in other words, we could set the terminal velocity that we wanted to shoot that rail gun at by adjusting our battery and our magnetic field, and of course the link between the two rails. Now, I will warn you about this now. Notice this formula that we end up getting for the induced EMF for this particular system. B, L, D. I will warn you that it is not a catch-all. It's not a catch-all. It doesn't work in all situations. Okay? But there are many situations in which it does, which is why your book discusses it. And your book gives you a completely different scenario. One scenario that you can look at in your textbook is the generator with the slide wire generator, which will end up with this same type of BLF type thing. BLV for the induced EMF. And the other one is what they call the motional EMF. Now for the motional EMF, I'm not going to go over the general form of it. Okay? Just too much for this level. Keep your book handy. When you get to the higher level, we can talk about motional EMF. For motional EMF, we have a rod just moving in a magnetic field. There's a problem on Mastering Physics. It's one of those tutorial type problems. Talk about it. The rod has some length L. Magnetic field is B. And it's moving with a constant velocity v. Now here is when this works. Okay? Well, no, I'll derive it first. And then. All right, so what we do is we say, what is the EMF induced in that rod? I mean, the problem is we can't really talk about the induced current, because whatever induced current would be temporary, because it's got nowhere to go. The current has nowhere to go in this rod. It's just a rod, it's got a length L, that's it. Current, can't talk about current. But we can talk about an induced EMF, because the formula that they say is a mathematical formula that talks about any loop. It doesn't have to be a current loop. It seems more practical when it is a loop through which current can actually run. That does seem more practical. But in theory, it still works. So what we do is we draw this hypothetical loop. So it looks like this. Here's the loop. This, and as this moves, the loop is going to increase. As this moves over with velocity v, the loop through which we're talking about the magnetic flux is going to increase. And because none of the voltage could be taken up by the nothing, all of the voltage must be in the rod itself. All the voltage has to be in the rod because there's nothing here to take it up. So whatever voltage that is induced has to all be on that rod because it can't be taken up by the nothing. So there we do have to consider the fact that there's a nothing because the nothing is... So here I don't have to neglect anything because there's nothing to neglect. There's the nothing. So I can just move this through. Okay, so what happens is that I could use the same mathematics that I did before. Define this as the distance x. Find out what dA dt is. And what I get is I get that the induced EMF is equal to the VLV. And that's my motional EMF. The sense of that voltage, if I were to take this and move it over to the right here, the sense of that voltage in this loop that I've drawn here, let's see what direction the current would flow if there were rods and things to make the current flow. Okay? So I move this over to the right. My flux is increasing. Increasing flux in means that I want to make flux out. Make flux out by making the imaginary current counterclockwise, or just say that that's the sense of the voltage is counterclockwise. So in other words, this would be the high voltage end and that would be the low voltage end. This would be the high voltage end and this would be a lower voltage. That's the induced voltage. Now, you might think, oh, wait a minute here. I drew this in some totally ambiguous way, right? Totally ambiguous. And either you're too tired to question it, which is great. I'm actually going to help you for later on when you become more inquisitive and think, well, what? Just any loop. Forget it. So let's draw another kind of simple loop using the same situation. I'm going to draw another theoretical loop, if you will, okay? And show you this still works. So here's my rod. Here's the rod here, moving with velocity v, and the magnetic field is going into the page. Okay, those are the three things that are set. Okay? But that hypothetical loop that I drew is not set. The loop I drew is not set. So let's draw another loop. I want to include the ends here. And so now my loop's going to look like this. Ooh, look what I did, see? Okay. Now what I've done is I've included both ends. So I have the rod over here so I can isolate its voltage, because I want to isolate the voltage of the rod against the nothing. And now this is going to move. Well, let's see if we can get the same answer that we did before. So remember back up here, the sense of the voltage was that this is the high voltage and this is the low voltage, because current there would go counterclockwise. Okay, we want to see if we get the same thing with this loop, the same physical result with this loop. In other words, just because I changed the loop shouldn't make any difference, any in Faraday's law. Because it doesn't really say what loop you're integrating over. It doesn't dictate it. See what I mean? It does not dictate the loop. So therefore I said, well, we'll just do this. Ha-ha. All right, so we have V moving this way. We've got this linked out. Now, we can do the same thing we did before, except for this time I'm going to define this X right here. My dA dt would almost be the same, except for, in this case, it would be a negative sign. Okay? So it's minus LV, because minus L and dx dt is, dx dt is negative V, because the x is decreasing. That distance is decreasing. So I get a negative sign there. Okay? But that still wouldn't matter for this. The induced, the absolute value for the induced is still BLV. In other words, it's the same results here. The question is, do we get the sense of this right? Do we get the direction right? Okay, so we got that voltage right, or the amount of voltage that we're inducing. Do we get the sense of it right? All right, look, let's see what happens in this loop. In what direction is the flux? It's into the page. The direction of the flux is into the page. Is that flux increasing or decreasing? What, somebody mumbled the word. It's decreasing. Why? Because notice the area is shrinking. So I'm going to have less x's in this loop. So it's decreasing. See, for this loop, what happens is, as this moves, that gets smaller, so it's decreasing. So my loop has to produce a magnetic field in which direction to compensate? Into the page. Into the page. There's another way to get this without. If the flux is increasing, then the loop has to do the opposite of what it was. If the flux is decreasing, the loop is going to do the same thing as it is up here. So by looking at these first two answers, you can get the third one. And so finally, the sense of the current would be which way to make it go in? Clockwise. So the sense, what we call the sense of the voltage, or the sense of the induced EMF, is clockwise. Which means that, take your thumb, put it in, so around this loop, induced current would flow clockwise. Induced current would flow clockwise. Notice what that does. Because we got clockwise here, this end is a higher EMF than that end. And that same result that we had holds. That same result holds. Same result. Okay, so in other words, this is the higher potential, and this is the lower potential. So the same result holds. Now, there's another way to look at this in terms of what ends up creating this EMF that we end up getting. What ends up creating that. Because the rod has charges in it. If it's a conducting rod, it's going to have charges in it. Those charges are going to feel a force from the magnetic field because they're moving in it. They're moving in it. So they're moving this way. What happens is positive charges will end up moving toward the lower voltage. Negative charges would end up moving toward the higher voltage. So this is the problem that you have in your mastering physics. It's kind of an exploratory problem that you're going to look at. Looking at this motional EMF from the view of the moving charges inside the rod itself. Cool. Okay. Good. You can read about eddy currents. We're actually going to skip eddy currents in terms of what we do mathematically, and there's no formulas in it. What generally happens with real objects or physical objects is they're not nice and confined to a loop, or they're not nice and confined to some one dimension. A real object would be some piece of rod or a metal, and you can have in all three dimensions different ways of currents to flow. So it kind of does, so that kind of a bit more confusing in terms of which direction currents flow when they get induced. Okay. Now there's one more thing that this chapter goes over, and I'll go ahead and add it here now, instead of saving, and I could save it for the end after all this. But I want to take a look at these, go back to all of our theoretical equations for electricity and magnetism that we have so far. Okay? So we have four. They're great and they're nice and symmetric. So we have the integral. E dot dA is, this one, Q enclosed over F long line. That's the first one. Second one, integral E dot dl equals, well, once upon a time that was 0, but now we know that we can create a voltage by changing magnetic flux, so we have to include that. So it's our minus d phi sub b dt. Then we had the integral of b dot dA equals 0. And then Ampere's law, B dot dL is equal to mu naught multiplied by current, of course. It's our Ampere's law. There's one thing missing from this. What we have, notice is we have a source of electric field, charge. Source of magnetic field, current. So far so good, right? Source of electric field, charge, magnetic field. We also have having changes in magnetic fields creating electric fields. Now, if these two things are of the same nature, then there should be some symmetry involved. So what's the converse of this? Changing magnetic flux, creating electric fields. What's the converse of that? Yes, changing electric flux, creating magnetic field. Changing electric flux, creating magnetic field. And to get that, let's look at Ampere's law again. We'll look at Ampere's law. Okay? Now, let's have a long straight wire. Okay? Except for this one little thing I'm going to do with this long straight wire. In the middle of this long straight wire, I'm going to have a charging capacitor. There it is. Ta-da! Charging capacitor. It's in the middle of my long straight wire. So I have my long straight wire, and I have my charging capacitor. All right, now I'm going to draw my Ampere loop, the loop around this current that I'm going to have drawn. So here's my loop, like so. Okay. That's behind the base. There it is. That's my loop over which I'm going to integrate to get my magnetic flux. I'm going to use Ampere's law and integrate over that loop. Now, the thing is about this loop, and when we call about the current that penetrates that loop, or the current that's enclosed by that loop, it doesn't matter what the shape of the area is, as long as this loop itself subtends it. In other words, if you're talking about a cup, it doesn't matter whether you take the top of the cup, that circular area, or the rest of the cup itself. I can take the rest of the cup itself. Mathematically, it should make no difference. Except for coffee tastes better than capacitors. So if we took this standard area here, the current penetrating the loop is whatever current's flowing through this wire, I. Right, I've got a current I flowing through that. That current is what's going to penetrate it. Well, what if I then, instead of taking that area, did this? This is the area. There it is. There's the area over which I'm going to do it over this bowl area. Okay, I'm going to do it over this area. This, can-shaped area. That still stays that loop. That loop defines the ends of that area. So therefore, mathematically, it's the same thing. How much current is flowing through that loop? None. there's no current flowing through that loop because it goes into the gap of the capacitor. There's no current in there. There's no current in the gap of a capacitor. I mean, the current stops here and it starts over here. Charges flow onto one side and off the other. It doesn't go in between. Oops. So when you do this integral over this loop, and notice the integral's over the loop, not the area. So if I do the integral over this loop, I could get one of two things. Wait a minute, that can't be. I can't get two things. I can't get 0 and mu naught times I. I can't get two things. One of them has to be correct. So all I have to do is measure and say, yes, there's current. I'm getting a magnetic field here. So the 0 is not correct. If we have current flowing here, there's going to be a magnetic field there. The capacitor doesn't cancel out the magnetic field. A long straight wire. I mean, we could imagine an extreme situation where I have the magnetic field and my wire over here, and that capacitor's way over there. I can still make my area, because it's a mathematical area, I can do anything with it I want to. I can go all the way over there to connect it through the capacitor. Because it's mathematical, it doesn't matter. But physically, we have to be consistent. So this has to be fixed. This must be fixed. And so what we do is we define something called displacement current. We define a displacement current. What is going on inside of here is that the charge is changing. Okay? Because the current is equal to dq dt. So the charge on my capacitor is changing. Now because that charge is changing, I have a changing electric field inside of the capacitor, which means I have a changing electric flux through the capacitor. And it's that changing electric flux that we look at when we talk about the displacement current. So it's this changing electric flux through that loop. Oh, it's my alarm. Sorry. Fix this. All right, so what we do is we can figure this out, and so what we do is we define a displacement current as being epsilon naught for a vacuum, change in electric flux,
What's the subscript next to I?
D for displacement current. And then we separate this current and we call this conduction current. Conduction current is moving charges. So then we can fix up we can fix up Ampere's law by adding the two types of currents together. So in other words, if I do the integral, if I consider this blue area here, I'm talking about the conduction current. If I consider the orange area, I have the displacement current. So it's actually the sum of the two that gives me the total current. Because theoretically I could have, like if this broke down and I had some charge going here, but it's still charge accumulating, you could get fancy. So we just add the two together. So we finally fix this by saying the integral dot EL is equal to mu naught multiplied by I enclosed, except for now, what we tend to do is we simply say conduction current plus displacement current. And if we were to write that out, we would say mu naught multiplied by conduction current. And don't panic about conduction current. Okay, conduction current is the current that we've been talking about all along, moving charges. That's conduction current. Conducting electricity. That's why we call it conducting current. Displacement current, we're not conducting electricity because there's no actual electricity moving where there's displacement current. It's changing electric flux. plus mu naught epsilon naught d phi sub e. So that then completes the symmetry of these equations. And so these equations get wrapped up together and they're all called Maxwell's equations. Maxwell's equations. You could delete the last 2 minutes of silence there. We're done with this chapter, and so what I'd like you to do is go ahead and get in your groups, because I will be posting a group assignment for you all. You need one more for the test. Oh, and there's one thing I wanted to mention.
Due on Monday, right?
Yeah, due on Monday, yes, along with the rest of this homework that you guys haven't started. So also use this time to start your homework. There's one thing about the test that I want to make this third midterm, is that while I will be posting a formula sheet for you, that will be a starting point and you can add to it. Okay? That will be a starting point you can add to that formula sheet.
And bring our own.
And you can bring your own. You can bring your own. In other words, we've gotten to the point now where there's so much material that you can go ahead and start making your own.
So we can like write on it?
Yeah.
And like name the formulas?
You can name the formulas, yes, that might help. And put some units there, that might help. And put what the mu and the micro and the nano and all that stuff means, that might help.
Can we do it all in a?
So can TOA can help. Yes. Well, just one piece of paper front and back is fine. Yes?
On the last test you gave, that showed top problem before that test was on the.
Those problems are still, if not there, I'll look for them and put some up for you, okay? Yeah, that's what he was talking about.
Oh, he did.
Yes.
No, I mean like before things like,
Oh, those specific? Unfortunately, this one isn't as clear cut as those ones were, because this one is another one of those theoretical chapters, whereas that second test mapped out nicely with the, you had the resistor and the capacitor, and there was just a certain type of problem that, that you always did. In this case, I can tell you there's going to be at least one problem from each chapter, so there's going to be one problem where you're talking about particles in magnetic fields moving, and you're looking at the forces on those particles. There's going to be one problem about generating a magnetic field. In other words, currents used to generate magnetic fields. And there's going to be another problem where you're talking about Faraday's law and induction. Okay? And I may have a series of smaller problems where I'm simply asking you to use Lenz's law. Like I might ask you 2 or 3 different Lenz's law questions, or I might ask you to explain Lenz's law in terms of what's going on with the magnetic flux, just like we keep doing it here. And I will drill in your head Monday after everybody does their homework. So those are the problems I really want to hammer in with Lenz's law, is how to do that. Yes, go ahead.
Could you quickly go over the right-hand rule that we're going to use now?
Sure. Plenty of them. Plenty of them. The right-hand rules spawn from the cross product. That's why, it's in all these formulas, the generalized formulas have cross products in them. So in other words, where you have your force of the magnetic field, QV cross B, okay, you have a cross product. So as a general rule, when you're looking at these, cross products. The first vector in a cross product is the straight fingers. Okay? So that when they turn, and that's why you do have to look at both vectors, because you have to point these, yes, along the V, but you have to make it so that when they turn, they are in the direction of the magnetic field, or the second vector. Yeah, straight fingers in the direction of the first vector, so that when you turn them, they're in the direction of the second vector. And the result of those, so in this first formula, you've got this Q, though. You've got to remember that if that's a negative charge, then therefore you have to reverse it. Second right-hand rule we talked about when we talked about creating currents. This one does come from the Biot-Savart law, and I could use the Biot-Savart law to show you how this works, but it's a little easier to do when you're talking about currents like this, when you're talking about currents, to actually the two of them. The current, the magnetic field generated by current will loop around that current in a sense given by the right-hand rule. So in other words, if I put my thumb in this direction here, then it's going to loop around this loop clockwise like this, or counterclockwise. Drawing three-dimensional perspective drawing here, okay? Concentric circles. So for that one, the thumb goes in the direction of the current, and the looped fingers are in the direction of the magnetic field. And so you have to remember that in this case, it's magnetic field generated by the current. Generated by the current. Now for this one, we could use that same magnetic field rule to realize that the magnetic field is looping around this current, because it really does. So let me draw the magnetic field here. Looping around this current in a sense like so on this side. So in other words, here, it's going to loop around this way. And over here, the current will be coming back out like this, so it'll be looping around this way. Like that. So the magnetic field actually does loop around this wire by using this right-hand rule over here. However, because we so often want to find the magnetic field in the middle of this loop, and the reason, and you can see why we so often want to do that, because that's what we're talking about. We talk about Faraday's law. What's going on inside of this loop? The magnetic flux through the loop, the magnetic field that needs to be generated by the loop. That's why we always want that inside the loop one. So the inside of the loop, quick and dirty trick, tells you to put your fingers in the direction of the current. Your thumb will point in the direction of the magnetic field inside of the loop. In other words, it's the reverse of this one. The reverse of your long straight wire. But that, of course, only explains inside of the loop. So in other words, inside the loop, the magnetic field goes up like this. Inside the loop. But notice you do get that from here. Notice because when you get to the inside of the loop, it's going up, outside it goes back down. Inside it goes up, outside it goes back down. So if I can do this. So this is what it really looks like. So those are the main right-hand rules that you're using. The main right-hand rules you're using. else before I send you off to study? I do want you to finish your homework Monday. We'll be spending the time Monday going over most of the problems, especially those Lenz's Law problems. There are several Lenz's Law problems. I want you to get lots of practice with Lenz's Law. Okay? And just remember the way that we ask those 4 questions. And then once you get used to it, you can kind of get a sense of, well, okay, what's going to happen here, what's happening here, what's happening here. And you can start to do them in your head more or less. But that's a long time after now. So I'm almost teaching this, unfortunately, like Common Core. So even if you get it, I still want you to do it the Common Core way and tell me the flux is into the page, it's increasing, and therefore I have to make flux out of the page, therefore it's going to go counterclockwise. That's what I want you to do. Okay? Because you could just guess 50-50, and I don't, like, that's not really learning anything, that's just guessing 50-50. That's why I want you to. Well, let's do an example before we go. Magnetic fields pointed out. I don't use magnetic fields pointing out very often, so I'm going to use magnetic field pointing out. Since you guys seem just so tired, you want me to do another example? We'll start on this one. Let's see. What do I want? Bless you. Let me put a triangle. Yes, triangle, okay? A triangle. I'll make it a right triangle. There we go. Right triangle. Let's say that this distance here is 40 centimeters, and this distance is 30 centimeters. Okay? 40 and 30 centimeters. And I'm going to pull this out of the magnetic field with a velocity of v equals 10 centimeters per second. Ta-da. Okay. And then for this question, I want to know what is the average induced EMF as I pull the loop out. As I pull the loop out, what is the average induced EMF? Okay. All right, let's take a look at that. Since we want average here, we want to be careful. This is a situation where BLV is not going to work because everything is not perfectly straight here. It's a triangle. Okay? If this happened to be a rectangle, then BLV works. Then the BLV works if it happens to be a rectangle because it looks like all those slide wires and all that stuff that we've been doing with just a rod. But since it's a triangle, this kind of messes it up. But it's not that much of a problem. Let's get a little variety here. Let's say that I have 30 loops that I've made into this. So my induced EMF, on average, is, I'm going to use absolute value, is in d phi sub b dt. In d phi sub b dt. Magnetic field B, let me give it to you. I don't know, 0.25 Teslas. Like a large magnetic field. Okay, so the number of loops is 30, and now I want the change in magnetic flux. Well, the change in magnetic flux here, I want to get from a before and an after. I want to use the delta, not the d, because I'm asked for average. I'm asked for average. So after, what's my flux after this thing? So after, this is after it gets pulled out. What's the magnetic flux? Somebody better be able to answer that.
0.
0. I pulled it out of the magnetic field. The flux is 0. So that's 0. Okay? So my n is 30. My final flux is 0. So P final minus T initial divided by delta T. My initial flux is the magnetic field multiplied by the area multiplied by cosine phi. Magnetic field here is 0.25 Teslas. How do I find my area? 1/2 base times height. So it's 1/2, 0.4 times 0.3. That's my area. Cosine of phi is what? The other way. 1. Okay? So somebody multiply this out. Tell me what you get, because I don't know what it is. I just made up the numbers. I have no clue.
.015.
0.015. Sounds good. And this is Weber's or Tesla meter squared. Either one is acceptable unit for a flux. Okay, now we need to figure out delta T. How would I find that? Anybody know what delta T is? Can you tell me what it is? I know just by looking at my given
4
information.
seconds.
How many?
4.
4 seconds. It's moving that way, its velocity 10 meters per second. In order to get out, it has to move over 40 centimeters. So therefore, 4 seconds. So that's the other thing you have to find. Here's the delta T. Delta T is equal to 4 seconds. You can just plug and chug to get that, to get what that turns out to be. A couple other things I wanted to ask you. Let me try. This is the average induced voltage here. If I were to look at the induced voltage as a function of time, okay, just the absolute value of it. Would it do this? 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 That's good enough, right? I think that's all the different things I could think of that do it. I can think of more. Which one of those is right? Which one? And how do you know? Well, let's go back and look at it. At first, when I start pulling this out, because I'm moving with the constant velocity, right? So the increase in area here is going to be smaller. When I get to this side, it's going to be larger, 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 and then finally, once this gets out, it drops to 0. So it's this one here. So it's that one right there. And that's how it looks as a function of time. Okay. I could specifically have you calculate that because I know you're great at calculus. You could actually do that here.
No.
All right, get in your groups. Talk to each other.